Let's get into this example right here. In something like this, one main place where I could expect to find it written with mistakes for one main reason is that the leading term is negative, and when people are solving, they will assume that it is positive because maybe that's what they're used to, and they will not write steps. They will do certain things in their head and jump ahead, and they will get the wrong sign for the number on the other side of the equal sign because they'll think, oh, add 3 divide by 5, 3/5, right? But it's a negative 5. And I always find it fascinating that, I mean, it makes sense, but I don't know why people don't fix it. The people who tend to show their work don't make mistakes. And the people who don't show work are always making mistakes and getting lower grades. Like, why are you trying to skip so many steps and act like you're like a mathematician from, some foreign universe, right? You're human. Just show your steps. You probably won't mess up and you'll probably be better at math, okay? So let's all get on this. Let's try a little harder. I constantly tell everyone to factor a negative all the way out, and you guys just don't listen. And it's weird because it's like you're just okay with being lazy and constantly getting the wrong answer. Like, what's the thing? It's like, when you keep doing the same thing over and over and expect different results, that's a sign of insanity or something like that. So come on, guys, let's get it. All right, so let's show you what it would look like if you did it properly. You would add 3 to both sides. You would not get lazy. You would pace yourself, negative 5x squared. Watch when you write 5s and 3s in the same problem. Some of your handwriting's pretty atrocious, and they look alike. And I can't read it. You can't even read it half the time. We're going to, I have another thing. From this step, what I see all the time, not good. I see, you see -5, but it's -5. And I know sometimes like we're a little loosey-goosey with that language and that speech describing numbers, but it's a -5. So it's attached to that x squared with multiplication. And to get it separated from that x squared, we have to use an inverse operation, which is division. What will people do? Add. Because they see -5 and they think, oh, +5. No. Don't do that. Don't you dare. Don't you dare. We're going to divide both sides by -5. X squared equals. Now, I see this all the time. It never sticks, but maybe for one or two of you it will. Please don't leave a negative in your denominator. No one does that. It's kind of like the radical thing. You don't leave those in the denominator. So it's really okay to just move a negative up to the top in a situation like this. If we have a sum or difference in either our numerator or denominator, we will have to play with it a little bit, factor it out in a way. But I'll show you that in another example. We don't have time for that right now. Just keep in mind it won't necessarily be that simple. Here we are with -3/5. Now, in this example, yay, we get to practice rationalizing our denominator. Hooray! So we are almost done. We're going to take the square root of both sides. On the right side here, we are going to throw that plus minus out front. And this has a little hook because it's a radical. Division signs don't have that. Next, x equals. Okay. Earlier, in another example, x squared equals -7. I talked about how the square root of a product is equal to the product of their square roots. New sentence. The square root of a, what do you call the answer to a division problem? Quotient. The square root of a quotient is equal to the quotient of the square roots. So the square root of a quotient is equal to the quotient of their separate square roots. So we're right there. Now there's no need to put plus, minus, in front of both the top and the bottom, it's redundant because plus over plus is plus, plus over minus is minus, minus over plus is minus, and well, minus negative. I just said this, right? And negative over negative is positive. So you're still going to get both the plus or positive and the minus or negative. So, we could just write it once in front still. In the event, store this in your memory bank. In the event that you have plus minus going on somewhere and you divide everything by negative, plus minus becomes minus plus, which is still plus minus. Think about that. All right. Anyhow, well, what do we got here? 3 and 5 are both prime numbers, and I don't have anything I can really simplify except I can deal with the negative underneath my radical. So I have x equals plus and minus, or positive negative, I root 3 over root 5. Now, answer's looking better. We fixed the one issue, which was a negative under our radical. We still have another issue, though. We're not allowed to have a radical in the denominator. How do we get rid of radicals? We need them to be squares underneath the radical. We need a perfect square. But you cannot, guys, you cannot just randomly square a fraction. That's not a thing. Like, if you had the fraction 2/3, and you're like, I feel like squaring it. That's the same. No, it isn't. No. Could I multiply the top and the bottom, or numerator and denominator, by 5? Yes. What does that give us? 10 over 15, which will still reduce to 2 out of 3 because of, multiplication and division and how fractions work. But if I take that same 2/3, which is 0.6666 repeating, and I square it just because I feel like it, that would give me 4 over 9. And 4 over 9 is 0.44444 repeating, not 0.6666 repeating. They are not the same. You cannot do that. So squaring a fraction does not retain its value. Multiplying it by 1 does. Hence the phrase multiplicative identity. It's what you can multiply by and maintain the same identity. So what are we going to multiply on top and bottom, or in the numerator and denominator by? By square root 5, because that ensures that my denominator is a perfect square. This is kind of the reverse of the 7, -1 thing, right? The product of square roots is equal to the square root of the product. So the square root of 5 times 5. 5 times 5 is 25. Square root of 25 is 5. But no one writes all that. Just square root of 5 times square root of 5. In your head, that's square root of 5 squared. And square root and square, bye-bye. All right, inverse operations, sayonara. And you're just left with a 5 on bottom. Last but not least, x equals plus minus I root over, so that's 5. But what about the top? 3 and 5, same thing. They multiply. They're both square roots. If one were a square root and the other were a cube root, a little bit different. But they're both square roots, so we call those like radicals, and we're good to go. So square root 3, square root 5, that's square root 15. Can we reduce the 15 and the 5? Absolutely not. We can only reduce things that are both under radicals, top and bottom, right? Or we can reduce the things that are not underneath a radical. If this 3 over 5, or over 5, if it were written as separate radicals, but it was like 30 and 5, we could reduce, because this can backtrack to that, and we could reduce underneath. So think about these things. Simplify, make smaller, make easier. Don't overcomplicate things, okay? So those are our 2 answers to this one. I hope you like the example popping up on the screen for you to check out next. If not, go to the playlist, find one that you do like, or figure out what you want to be working on. There's only a few more examples in this set, and I hope you've been watching from the start and are doing an excellent job. All right, see ya, or you'll see me in the next video. Sayonara.